Welcome back, Geos 406 students. This is kind of an interesting module. In this module, you're going to estimate the volume of a debris flow from the Panabaj, Guatemala region. Um, this flow happened in response to a tropical storm. It is a debris flow from a volcano. It just was triggered by a non-eruptive event. You're also going to be asked to do some sort of hazard analysis and forecasting for debris avalanches from Mount Shasta. So accompanying the lecture on lahars and debris flows, a debris flow is a mixture of rock, debris, and water rapidly moving downslope because of gravity. These can be very fast. It can be a lot of volume, a lot of force, so they're very destructive. They can erode the channel, they can bury and sweep away buildings and roads and bridges. On volcanoes, these can form very easily. You have mobilization of loose volcanic material. It can happen during eruption or after eruption, primarily due to heavy rainfall or melting snow and ice. You can have seismic activity that helps trigger these events. At any rate, these are very common and very hazardous phenomena coming from volcanoes. So debris flows can be pretty big. There was a really tragic event in 1985 in Colombia. There was a debris flow triggered by a small eruption of Nevado del Ruiz volcano that melted snow and ice at the summit. The debris flow swept down the Rio Azufrado River Valley. It had a volume of about 4 times 10 to the 7th cubic meters, and it basically buried the town of Armero. So the magnitude of debris flows is often characterized in terms of volume. So the volume of debris flows can vary a lot. You can have small debris flows that occur really frequently. You can have very large debris flows that typically don't occur as frequently but can be very destructive and devastating. So we use an empirical estimate to categorize debris flows. And this is a little bit of review for you guys from the lecture. This is the vertical drop, or H, divided by the run-out length or travel distance, L. And this is a measure of how cohesive, or, well, you can think of it kind of like the viscosity of the flow. If you have a really fluidized, fast-moving flow, it's going to have a very long run out, or L, big L, relative to its collapse height or vertical drop. That'll create a low H on L. So that would be like, pyroclastic flows shown down here on this graph, the H on L of 0.02. Very stiff, sluggish flows that don't travel very far but can have pretty appreciable collapse heights would have a high H on L of 0.5 shown here. So this characterizes a lot of non-volcanic landslides and everything in between. Most volcanic debris avalanches fall on an H on L around 0.1 to 0.2, some maybe 0.05. So for the first part of your homework, you're going to look at a situation around Mount Shasta, California. Here's a picture of Mount Shasta. It's a really pretty stratovolcano complex located in Northern California. So it's 4,317 meters high. It's pretty active. It's had 10 eruptions during the Holocene, which is basically the last 10,000 years. The last eruption was 200 years ago, not that long ago. Produced a small ash cloud, pyroclastic density currents, and debris flows. But 300,000 years ago, Mount Shasta had a sector collapse. So basically a whole quarter of the volcano slid away and produced a huge debris avalanche. It was 26 cubic kilometers in volume and had an approximate run-out distance of 50 kilometers. So that's about 30 miles away from the volcano. It's actually a pretty hazardous situation for people living around Mount Shasta today. And you can see that from this map. On the upper left corner in the photo here, you can see this lumpy terrain. Here's Mount Shasta. These big lumps are debris avalanche hummocks from that 300,000-year-old event. You can see they're pretty big. They're scattered pretty far from the volcano. In the lower right, you can see debris avalanche hummocks here. And there's a highway that goes around them. There's city and towns nestled in amongst them. with Mount Shasta looming in the background. So this is actually a pretty big hazard from Mount Shasta and volcanoes like it around the world. Okay, so your first part of your assignment, which is described in detail in the Word document that accompanies these PowerPoint slides, is to do a simple hazard assessment for Mount Shasta for debris avalanche hazards. So for this part of the homework, you're going to refer to this map image on the left hand side. It's a USGS publication that shows the extent of this Pleistocene age debris avalanche deposit and similar deposits from Mount Shasta. So the green circles are blocks of Mount Shasta avalanche, or Mount Shasta edifice in the avalanche. So these are, the Torreva blocks that came from the collapse of Mount Shasta. So Mount Shasta is shown here. This brown stippled region shows extent of debris avalanche deposits from past events from Mount Shasta. You can see that it basically covers the region occupied by several towns, from Edgewood, Gazelle, Grenada, Montague, and so on. Wairika lies outside of the area of deposition, as does Mount Shasta City. So you're going to use this map. You're going to do some simple H on L estimations of runout length for given assumed H on L coefficients of debris flow sliding. And you're going to estimate some simple hazards based upon the debris avalanche reaching these different towns for different H on L predictions. So the second part of your homework assignment comes from the module developed by Chuck Connor. And in this, you're going to do a simple debris flow volume estimation given an aerial map of debris flow deposits. So in this graph shown on the right here, you have area covered by a debris flow in square meters plotted against volume of the debris flow in cubic meters. You can see these red dots. These are from a bunch of different lahar and avalanche deposits measured from a bunch of different volcanoes around the world. And you can see that the area covered by a debris flow scales with its volume. You can basically think of this as if you have a volume of material and it's entering a river channel or a drainage, the volume is going to determine basically how far and how wide the deposits settle. So that is, the volume of debris that flows off the volcano will be an excellent indication of the area around the base of the volcano that will be covered. It seems pretty intuitive. From a hazard perspective, this is really important because you can estimate the potential volumes of future debris flows from a volcano based upon the past record of areas that were inundated by prior flows. Okay, so I know I'm going to mispronounce this name, so my apologies. The Panabay debris flow happened in October 2005. There was a tropical storm in Guatemala that basically triggered heavy precipitation in the mountainous terrains, especially around volcanoes in the volcanically active region in Guatemala. So Lago de Atitlan is a Holocene caldera. It's shown in this photo here by Chuck Connor. It's rimmed by young composite volcanoes, and San Pedro volcano looms in the background. So in this situation, you had a community that was inundated by a debris flow from Toliman volcano. And it buried much of the community, and it was actually a fatal event, as these debris avalanches and lahars often are. So you're going to do an exercise where you estimate the volume of this debris flow from a map provided in this module by Chuck Connor. Okay, so during this tropical storm, mass movement on Toliman resulted in the debris flow, and you can see in this upper right photo taken by one of the Connors, you can see these streaky, muddy regions. That's where the debris flow originated. This bottom photo by Laura Connor shows the results of this debris flow as it came through town. It deposited in and among buildings that it had destroyed. The debris flow was moderate in size. It came down the volcano rapidly, which is typically the case with lahars. It broke out into two different stream valleys on the flanks of the volcano and continued to descend both of these channels until the flows reached an alluvial fan near the shores of Lago de Atitlan. So once reaching the alluvial fan, the flows spread out over a relatively flat surface rapidly and devastated a lot of the community of Panabay. So in your problem set, you're going to estimate the volume of the western flow. So here's a map provided for you for this exercise here. And you'll have two flows. So remember the debris flow bifurcated into two channels. There was one that went down an eastern flow channel, depositing the eastern flow deposit, and then a bigger, broader western flow deposit that came down a separate stream channel. And the lake is up here in the upper left corner. So they're termed western and eastern debris flows because of their relative positions where the flows crossed a paved road that runs through the community. So you're going to be given a map. It's going to be actually a little bit more detailed map with more detailed grid lines than this one. And you're going to be asked to estimate the area of the western flow deposit and then estimate its volume based upon thickness of the deposits. Okay, so you're given a map and flow thickness estimates. You're going to estimate the volume. So you're going to need to first estimate the area of the flow and estimate an average of the flow thickness. So you'll use this to calculate the flow volume based upon your thickness and area estimates from the map. And you're also going to be asked to estimate the uncertainty in your calculations. So error is really, really important in all sciences because it gives us a measure of how well we have determined something. And in this case, when you have hazard implications involved, the errors on your estimate for debris flow, inundation, and runout are critical because within that error envelope, you could have people living who might be at risk from a future flow event. So note, the volume of the flow is not the same as the volume of the deposit. So a large fraction of a debris flow is water. As the flow comes to rest, water and fine-grained sediments will actually segregate and will flow out of the primary deposit, causing that debris flow deposit to deflate and lose thickness. So this hyperconcentrated flow that emanates from the debris flow can go great distances downstream. So as a result, the deposit that you see in the field afterwards actually has much less volume than the actual debris flow that originally inundated the area. So you're going to need some additional information to estimate original flow volume, and that will be given to you. Okay, so here's the map you're going to use. You see that you have the two debris flow lobes. They're broken up into their different channels, and there is a grid. So UTM coordinates are given on the Y and X axes of this map grid. These are in meters. So the area of each grid cell can be estimated by figuring it out from the UTM coordinates. And I'll actually give it to you a little bit later in this PowerPoint slideshow. So you don't have to worry about that too much, but it is an important parameter. So you're going to need to think of a couple ways of doing this. First, you're going to need to estimate the area of the western deposit and its thickness. Then you're going to need to calculate the volume of the original flow and estimate uncertainty in your area volume and thickness estimates. So one easy way to do this is to divide up your map into equal area cells, which is what is shown on the right here. You can use the grid to estimate the proportion of each cell that is covered by the deposit, and then sum up the areas of each cell that you calculated. So the formula for doing that total summation is A, which is the area of the whole flow, is equal to A sub C times the sum of all of your cells, the total number of cells you measured, times F sub I. So A sub C is the area of each cell. F sub I is the fraction of each cell covered by the debris flow. Okay, so when you estimate area, it's important to also estimate the uncertainty of this number. So we're going to do kind of an eyeball method here. The way this is going to work is you're going to consider all of the cells of the map. You're going to look at each one separately. And then you're going to look at the fraction of each cell area that's covered by the debris flow deposit. So that's the gray in this western flow lobe, the light gray western flow lobe. Okay, so consider two cells from the map. That's shown down here, cell 1 and cell 2. So in cell 1, the whole thing is colored gray. That means this is easy. The fraction of that cell that's covered by debris flow is 100% in terms of percentage, or a fraction of 1. So in this case, your area fraction estimate for cell 1, so F sub 1, is equal to 1, and you're 100% certain that the whole cell is covered because the whole thing is gray, right? So your error is 0. That means that you know for certain that this cell is completely covered by debris flow. Let's look at cell 2. So in this case, it would be F sub 2, and you're going to eyeball this and you're going to say, I think it's about 80%. If you think 50%, I'm going to show my mouse cursor here, would be covered something like this, where I'm drawing this vertical line through half of the cell. You know that it's more than half, and you know that it's less than 100%, so you're going to say, okay, it looks like it's about 80% to me. I know it's more than 50%, I know it's less than 100%, looks like it's a little more than 75%, so I'm going to call it 80%. So your fraction F2 is 0.8 for this cell number 2. Now the uncertainty, this is a little tricky. So if I say, all right, I think it's greater than 70% covered, less than 80, or greater than 75% covered, less than 85% covered, that means that it could be 75%, it could be 85%, I'm not sure. So that extra 5% becomes your error. So in this case, your F2 is 0.8, which is 80%, plus or minus 0.05, which would be 5%. So that means it could be 75%, could be 85%. Get the picture? Okay, once you get into this, it's not too difficult, and you'll feel a little uncomfortable because we all want to measure things precisely. But for this exercise, it's important to say, I might not be right, I might be wrong, so I'm going to provide some estimate of uncertainty to my area fraction estimate. So the area of an entire cell is 10,000 square meters. So cell 1 is 10,000 square meters, cell 2 is 10,000 square meters. I'm going to give you a very simple way that you can estimate the total area here based on the summation. It's area equals area of the cell times F1 plus F2, that's the summation. So that's equal to 10,000 square meters times 1 plus 0.8. And the uncertainty is delta A equals 10,000 times 0 plus 0.05 in square meters. So you're going to do this for each and every cell covered by the western flow lobe after its point of deposition here. This map is given to you on slide 24, and also it's linked up in Blackboard. Okay, so you also need to know thickness. So thicknesses are given on this slide. You're going to estimate the average thickness of the western flow lobe. So this map is showing thicknesses in centimeters. Use these data to estimate an average thickness of the flow. So you're going to note the flow thickness varies rapidly, and there's not enough information to make contour variations in thickness. So you're going to assume a uniform thickness in the deposit. So clearly that's not completely correct, but take your best shot and also estimate your uncertainty on this number. So essentially what you're going to do here is take all of these thickness estimates for the western flow lobe, and you're going to make an average. You're going to say, all right, what's the average of all these thickness estimates that I know are directly from this flow lobe? You don't need to do the zeros out here because they're not going to add anything. You just do the ones that are in this western flow lobe. Okay, so now, as I mentioned before, debris flows will dewater. So when the debris flow inundates an area like it did in this case, you have a high water line. It's shown here on this building right here. And then you have the deposit, the top of the deposit, which is much lower than that. You can see that. That's because the debris flow will inundate and then it dewaters and deflates. So in this case, you have a little thickness gauge here starting from 0 meters up to 1.67 meters on the left side of your slide. The high water line occurs at 1.67 meters. That's up here on the side of this building. The top of the deposit is 1 meter. So that's this elevation here where that debris flow ended up dewatering. So in mapping a deposit, the volcanologists in this case determined that at most locations, the thickness of the high water mark adds about 40% to the total deposit thickness. So volume of the debris flow becomes V, volume equals area, times 1.67 times T sub m. That's the average measured thickness of the deposit. So basically you take your measured deposits and you inflate it back up again to account for all of the water that was lost. Okay, error bars are really important. As I noted before, if you are trying to estimate future hazards from a volcano, you can't just stick with one number. You need to know the error envelope, because if you have an event that exceeds your number, but it's within some uncertainty of your initial estimate from deposits from a prior eruption, there may be people living inside of that sort of error envelope. You need to account for that if you're going to properly warn people of risk from a volcano hazard. So you're going to need to estimate your uncertainty in volume. So given all of your estimations, how certain can you be about volume estimate? You know you're uncertain about your area. You know you're uncertain about deposit thickness. So you're going to calculate a delta V, a volume error envelope. So in this equation, you have delta V, that's the error on your volume. It's equal to your calculated volume times a sum here. Delta T sub m, that is your deposit area your deposit thickness error estimate, divided by the thickness, so that's the average thickness, plus delta A, that is the total sum of your error on your area calculation, divided by the error you calculated. So do your best with your error estimates on area and thickness to come up with your volume uncertainty. Okay, so you should create a spreadsheet that looks something like this. This is just an example. Don't copy this. I'm going to ask you for your map, your annotated map, so that I can see how you estimated your areas and uncertainties. And these numbers are not going to be what you're going to estimate. They're going to be totally different. So this is just an example of how to set your spreadsheet up. First, you're going to type in your cell number. You're going to type in your area fraction estimate for each of your cells. You're going to type in your estimated uncertainty that you estimated for each of your area cells. You're given the cell area, it's 10,000 square meters. You know that for certain, so this is going to be 0. The mean deposit thickness, that's the average thickness of the deposit that you estimated from the map on the prior slide, in meters. You're going to do your summation. You're going to sum up the area fraction of all your cells and enter it, and that'll be your calculation cell here. You're going to multiply that number times the area of each cell, which is 10,000 square meters, to come up with your deposit area here. You're going to multiply that deposit area times the deposit thickness, the average thickness that you estimated here, to get deposit volume. You're going to inflate that by multiplying by 1.67 cubic meters to your thickness to come up with the flow volume. Don't worry about the significant figures. I'm not going to actually ask you about that for this homework set. Just focus on your calculations. You're going to do the same set of calculations, but for your uncertainties here to come up with your area uncertainty and your volume uncertainty. Okay, so that's shown in this slide here. Propagate your uncertainties, and you'll use this to calculate the volume error on your volume estimate based on your thickness uncertainty and area uncertainty. Okay, so first I want you to read through the PowerPoint slides so you can understand the background and methods you'll use in this assignment. Read the Word document in detail that describes the actual assignment so that you know what you're going to be asked to do, and please ask any questions that you might have. You can either download and print a copy of the map. It's given in Blackboard and also on slide 24. If you do it this way, you can download and print it out, and then you can just write, you can annotate all of the cells of the western debris flow deposits just by hand on that map, and put your area fraction estimates down in there, and then you can just transcribe those into your spreadsheet. Or you can use a computer or even PowerPoint to mark up your map with your numbered cells and area fraction estimates. So whichever method you do, I'm going to ask you to turn in a copy of your annotated maps. Either you can take a photo of your printed copy that's annotated and uploaded in Blackboard, or you can submit your PowerPoint slide annotations or whatever format you want I just need to do this so I can verify your measurements and so that I can track your calculations, so that if you make mistakes, I can help provide accurate feedback. And again, if you have any questions, let me know, and good luck and have fun.